Good afternoon, everyone. We will start in 1 to 2 minutes time. Alright, good afternoon, everyone. And today's intermission session, for lack of a better name for this session, is going to be focused on any particular topics that we've covered so far that require some sort of clarification. So feel free to specify which topics or which particular subtopics in the lectures that you may have not understood on the first pass when we did it. And we're going to take another crack at it to see if we can rectify all those misunderstandings or any things that you need some sort of clarification on. This is what this session is going to be dedicated towards. It's also going to be a good time for resolving these topics because at 9 p.m. today is when your first quiz is going to be released, as well as your first group assignment. And the quiz is going to be for 24 hours, and the group assignment will be due within 2 weeks' time. And they're going to be based on the material from lectures 1 to the end of lecture 7. Details for the quiz and the group assignment were posted on my learning, so anything regarding how long the quiz is going to be, what topics are going to come, the format of the quiz, and so forth. All those things are posted on my learning, and you're also invited to ask any questions in the appropriate forum regarding anything that required some sort of clarification for either the quiz or the group assignment. So if there's anything that you need to ask now from lectures 1 to lecture 7 that requires some sort of clarification, feel free to ask now. Alright, so we're going to request can we go over how O log n is found or proven. Alright, so I'm just going to bring up the lecture here on my side for the rectification to see where did we do this, and I'll explain it in a different form for you to understand how do we observe a log n fashion. One second here. Alright, yeah, okay. So let's go on about this O log n stuff that people are a little bit confused about, right? So we're talking about, I'm just writing here, O of log n, and this is what we're going to be talking about here, to rectify. So the simplest way to understand how we go about observing a log fashion, and basically when we use log here, it can be log of any base, is where we see that we have some sort of, we start with some large data set, and it keeps on getting divided by some constant factor throughout regarding its data whatsoever. So like, let's say if we had, for simplicity's sake, the easiest base that we could work with is log 2. Because In computer systems, everything tends to operate in binary fashion, which is 0 or 1, so that's to the base of 2. So that's the easiest one to operate with, right? So if we said n was equal to 32, being that n being the size of our data, size of, and I'm saying size of data here, but let's say this is the size of our array, and we need to find some particular value inside this array. The idea is, instead of having to go all the way from n equal 0 to 31, because remember, arrays start from 0 and end at n minus 1, so 0 to n minus 1. Instead of going in a sequential fashion, we're trying to figure out what's going to be the fastest way for us to figure out, okay, where would be this particular value. And a nice way of thinking about it is that if we had a balanced seesaw problem where we had the entire length here going from 0, 1, 2, all the way up to 31, and let's say we had 1, 1, 1, 1 going on here, but then we had some value here that's 3, 1, 1. And then we need to figure out, okay, where does this value lie such that instead of the seesaw being balanced, we know that the right hand side here is going to be unbalanced. So which part of the right hand side contains this particular value that unbalances the entire seesaw? So instead of having to go through it from 0 all the way up to 31, we can then do what we refer to as a half and half approach here for a log n fashion. So we can divide this in half, and we can be like, okay, for this particular half is everything balanced. And then for this particular half here, is everything balanced as well. So if this left hand side here only contains 1s, we can say yes, this is balanced, so we don't need to worry about the left hand side. On the right hand side here, this can be no. And then we know, okay, we need to focus on the right hand side some more. So if we focus on the right hand side some more here, you know, it's 3, 1, 1, then let's say, for simply say 29, 30, 31. We can divide it in half again and do the same balance approach. So the left hand side here is this balanced, and the same thing with the right hand side. Is this balanced as well? And this is no. Oh, sorry, this side is yes. And this side is no. So then we can just focus on this side again and can keep on repeatedly dividing it by some constant factor. So when we do that, when we have n here is equal to 32, and then we say, okay, we do this balance approach to figure out which side has this unbalanced factor. We reduce our data set from n equals 32 to n equals 16. So this was original, and this could be the second or first half of n. So we can, let's say, for simplicity's sake, let's call this n1. And we say this is n0. Then we can say n2 here is 8, because we divide this by 2. Then we divide this by 2 again. And we keep on going until we actually find where this value that is contributed to our unbalanced seesaw as to what is going to be where our value lies. And we can see here that for each step that we do, and let's just say that's the worst case where we go all the way down to 1, each step that we do here halves our data set. And in doing that approach where we keep on dividing by 2 throughout, each division can be mapped such that it goes back to a logarithmic form. So if we started here at 32, and we say, okay, what is log 2 of 32? And log 2 of 32 will be 5. And same thing, if we say log 2 here of 16, that's 4. Log 2 of 8, that's 3. Log 2 of 4, that's 4. And so forth as we keep on going. Log 2, sorry, not 4, this is 2. I mixed up myself. Log 2 of 2 is 1. And you get the idea as we keep on going along. So because each division here, where we truncate our data by half, and we watch the pattern at which we are doing it, we can form a mathematical notation to observe this pattern in order to see this. And this mathematical notation for observing the pattern here is what forms our order of log. So that's how did we come up in particular with us trying to figure out, okay, how does this reduction of our data follows what particular fashion, and what mathematical equation can we map it to represent this reduction. So that's how you end up getting that log n stuff. The converse is true like when you're going up in powers, because that's an expansion of your data. So for log is a reduction of data by some constant factor. So some constant division factor. If you were expanding your data, so let's say you had 1 and you went 2, 4, 8, 16, 32, then it's just going to be the inverse of a log, which is basically going to be 2 to the power some n factor here. But n is going to be your data size at which you're going to be expanding up to. So simplicity is that once you figure out what the pattern is for how your data expands or contracts, that basically forms the order of any particular equation that you need to map to regarding your programming statements and so forth. So it's really just watching how it is that your data is going to be expanding or contracting, or how does your data iterate throughout each other, or how does it recurse throughout each other as of such. So once you formulate some sort of mathematical pattern, that's basically going to be your order equation no matter what. Right. So hopefully that answers the log n stuff. If there's anything else to ask regarding this, ask now before I move on to the next question in the queue. And I just gave the example on the half approach here, which is basically the logarithmic form that I just now showed you. So a half and half approach is basically where you keep on dividing the data sets in a half and you keep on going. I'm getting to your questions in a minute, Jamar. I'm just waiting to make sure that if anyone has any questions on this log n explanation, so I can close off on this and I can get on to the recursive statement questions that you have. Alright, sure, I'll go over it one more time to give you the simplified version of it. So we're thinking about this in terms of like a balanced seesaw, and we want to figure out, okay, which side of the seesaw is unbalanced. So it's like saying for each index here from 0 to 31, if we have a data size of 32, we have on the left hand side, we only have 1, 1, 1, 1, 1, 1, and so forth. But somewhere on the right hand side here, we know that the seesaw is unbalanced, but we don't know which part it's unbalanced. So it's like if we have 1, 1, 1, 1, and then we have some weird obscure value here being like 3 or 4, and then we just have 1s after. So we want to find out where this value is on the right hand side for a seesaw, because we know if it's on the right hand side and the right hand side is greater than the left hand side, this right hand side is going to be going down physically like a seesaw. So instead of having to go through each and every index to find this, which is basically like if we're doing a brute force approach, there's a more optimized way of doing this. So if that's in this case, we say, okay, let's keep on dividing the seesaw in half and seeing which side is balanced or which side is unbalanced until we find out where this factor is that is unbalancing our seesaw altogether. So if we know the left hand side here only has 1s and the right hand side here has our factor, we can just check the left hand side here by dividing our data set entirely by half and say, okay, is this side balanced? Is it? Yes. Okay, so we don't have to worry about this side no matter what. But on the right hand side, is this side not balanced? And we say basically, see, is it balanced? No? Okay, let's only focus on this right hand side here. So in focusing on this right hand side here, we divide this right hand side again by half. And then we watch on the left hand side here of this. You'd be like, okay, is this side balanced? Yes. Is this side also balanced? Oh, okay. So then if this side is not balanced, let's only focus on this side here as of such. And we keep on doing this division throughout. Instead of having from 32, we go down to 16 values, then 8, then 4, then 2, and we go all the way down to 1 value. And once we have 1 value, we know for sure that is where our unbalanced factor is going to be throughout in our entire data set. So, because we keep on doing this constant division here by a constant divisor, because we start with 32, we divide it by 2, we get 16, and then we keep on dividing by 2 throughout 8, 4, 2, 1, we basically can see that in watching this formation here, or this pattern, we can map this to a mathematical equation. So in mapping this to a mathematical equation here, we can see that, okay, we always are going to be divided by 2. For each step here, let's see how do we map it so that we get whatever we need. So if we say log 2 of 32 here, this is here is going to be 5. Log 2 of 16 will be 4. Log 2 of 8 is 3. Log 2 of 4 is 2. And log 2 of 2 is 1. And we basically see that we get the same pattern that we had going up the road. Because we had 1, then we had 2, 4, 8, 16, 32. Same thing as we saw here. 2, 4, 8, 16, 32. And once we were able to match that pattern, we know that the order of this function, because it's logarithmic in nature for the pattern, the entire order of the function here is going to be logarithmic as well. So once you establish a mathematical equation for your pattern of how your data expands or contracts, or how it iterates or recurses, that basically forms the order equation that you need for any programming statements that you encounter. If you did the inverse, instead of contracting the data, so we started from some huge number and we went down to a very small number by a constant division. If we did the inverse, where we started with a small number and we kept on expanding, so that means that we kept on multiplying by some factor, it would end up being 2 to the power n, or 3 to the power n, or 4 to the power n. Whatever your factor is going to be expanding, that will be the base, and the power will be n accordingly. Alright. Anything else you guys need to ask about this logarithmic fashion? I think I got a good bit of questions here on the recursive approaches. So, as long as there are any further questions on the logarithmic fashion, I'll move on to these questions regarding the recursive approaches. I gave you guys an example algorithm in the lecture. Let's see which one it was. It should be in lecture 5. And that would have been for the binary search illustration. The space complexity for this would depend on how much memory you're using in particular. So if you're watching space complexity in particular, you want to see if you're going to be reusing memory or if you're going to be creating new instances of memory each time. Most cases when you do this, if you end up using the same amount of memory, so you're being very efficient, your order is going to be a constant factor, so it'll be an O to the 1. If you are duplicating memory as you keep on going, then because that memory is also expanding by a certain factor, then it expands linearly. So in that case, it will be O to the n. You will not get anything outside of O to the 1 or O to the n for this sort of thing regarding the space complexity unless your implementation is horribly wrong. In that case, if it is horribly wrong, you may end up getting something like O to the n squared. But in most cases, you will end up getting O to the 1 or O to the n. It really depends on if you keep on duplicating your data, or if you are always going to be operating with a certain amount of data no matter what. If it's that you're dividing your data by a constant factor here, meaning that if it was 32, 16, 8, 4, 2, and so forth, with the amount of data you're operating at in this particular case, and if your data is contracting by a certain divided factor as well, then the space complexity will also be O log of n. But if it's that you're using something else to keep track of this data, then you'll either be O of 1 or O of n accordingly. So it's really just analyzing where are you storing your data, and is this data being used? Sorry, is this data storage being reused, or are you creating new data storage for each instance to go about doing your stuff? So just to reiterate one thing, remember the example I gave you was a binary search, and I'm pretty sure you can find a lot of implementations of binary search in C++. Alright, doesn't seem like we got anything else queued in for our logarithmic approach. Let's move on to our recursive approach. So with the recursive approach, when you go with the bottom down and the top up, the bottom up approach and the top down approach, it's really how your equation is going to be mapped. So the perfect example for this is like if we said n factorial here, and we know that it's going to be n by n minus 1 by n minus 2 by going all the way down to 3 by 2 by 1. Now you may think, okay, because of the order of which this equation is normally written, you're starting with the largest value here, and you end with the smallest value here. And you may think, okay, you could go this way. And yes, that's fine, but you can also go in the reverse direction as well. Because remember, this is a multiplication. The order of the multiplication does not matter. So if we decide to go from the smallest to the largest instead, let's watch how we can actually formulate this recursively. So 1 factorial here. Oh wait, let's call this function here f of 1, and this is 1 factorial. So 1 factorial is 1. Then let's say f of 2 is 2 factorial, and this is 2 by 1, which is 2, or which is also similar to 2 by f of 1. F of 3 would be 3 factorial, which is 3 by 2 by 1, and we already have 2 by 1 here, which is 3 by f of 2. And we could keep on going on seeing our pattern, so I'll just wait for f of 4 here. Just 4 factorial, 4 by 3 by 2 by 1. This 3 by 2 by 1 is the same thing here, which is 4 by f of 3. So if we keep on going all the way down to f of n, this will be n by n minus 1 by n minus 2, going all the way down. And as we watch our pattern here from before, this will just end up being n by f of n minus 1. And it's easy enough to spot the recursion at this point because of this existing pattern. And this is if we took from the bottom-up approach regarding this. So it's easier to spot this if we took the bottom-up approach to figure out, okay, how do we go about formulating our recursion here? Because each one of these function calls, that I'm going to be underlining in blue here, represents our recursive function calls when you watch the code for your factorial. So that's an easier way to spot your recursions here, as of such, regarding the factorial function. The top-down approach would be like if we did it in reverse. And it's a little bit harder to see it in the top-down approach. Because it's like if we're saying, okay, f of n here is n by n minus 1 by n minus 2 by all the way down to 3 by 2 by 1. Then we have f of n minus 1 is going to be n minus 1 by n minus 2 by all the way down to 3 by 2 by 1. And then we can see here that f of n minus 1 here is just this part here as well. So if we also watch this for f of n minus 2, this is n minus 2 by n minus 3 all the way down to 3 by 2 by 1. And we can see here that this part here is also this part here as well. And we just do these substitutions as of such in order to keep on going about doing this. So as a result, let's zoom out a little bit. This will just be f of n. This here would be f of n. Sorry, I'm doing this wrong. This here would be n by f of n minus 1. This here would be n by n minus 1 by f of n minus 2, and so forth as we keep on going. So it's just going to be like a really weird way of observing it if we went from the other way regarding this. Now, a smart person will realize if you just watch these two here, you can immediately figure out the recursion for the entire equation in terms of n, because immediately you see it's n by f of n minus 1. So either approach is fine. One is obviously quicker than the other, but it always comes down to if you can see where we have these repeated function calls to formulate your recursion as a result. Yes, no matter what, the recursion function will be the same for both the top and bottom approaches. So if you go top down or bottom up, you will get the same recursion function. It's just going to be a difference in which of the order where you start from. If you're going to be starting from the smallest value to the largest value, or from the largest value to the smallest value. It will just be the same thing no matter what. It's also possible to rewrite these functions in a different way. So just to give you an idea of how we can rewrite these. So we saw there that f of n here was n factorial, and then if we did f of n minus 1, this is n minus 1 factorial, which is the same as n by n minus 1 factorial here. So this is if you're watching this regards if it was in decremental, right? But what if we went about doing it in an incremental style? So if we watched it such that we had f of 1 being 1 factorial, and then f of 2 here being 2 factorial, this is 1 and 2 by 1, and f of 3 here, 3 factorial, is 3 by 2 by 1. So this comes like if we had, say, n here, and then we had n plus 1 by n, and this is like n plus 2 by n plus 1 by n. And you basically can see how the pattern here is plotted regarding it as of such. So these sort of things is like, depending on how you go about doing it, you will end up getting like a different idea of going about doing these things in particular. Oh, okay. Right, so the base statement in these cases is how do you return your values? And the base statements are indicative of how you think about, okay, after you finish all the recursions, what value do you need to return for all the recursions to end up getting calculated properly? So for multiplications, in most cases, you just want to end up returning a value of 1. If it is an addition or subtraction, you will end up wanting to return the result instead. So I'm just going to give you that. So for multiplication, you typically return 1, because when you watch how the recursion operates, and you can review this back in our code operations tutorial, you basically see that all the functions here just keep on multiplying by one another. So it just keeps on multiplying until you end up with the last value, and you just need to multiply it by 1 to get back that value. The same thing with division. You can also return 1, because when you keep on doing these constant divisions, the last thing you want to divide by is 1 for your base case. So once you divide by 1, you'll get the actual result that you are required for. For an addition, or a subtraction, oops, writing that wrong, you want to return the actual result instead. And this result will be some sort of temporary memory storage that we saw in particular for that particular example that we also did in tutorial 1. Because if you return 1, you will just end up getting a value of 1 on your output. You will not get your cumulative addition value or your cumulative subtraction value from all the operations from before. So that's why it's important when you're doing an addition or subtraction, you need to return the result instead of returning some arbitrary value. The base cases are determined for where, if you're watching your if statements, the condition for the base case is determined where do you want your recursions to end. So if you're going from using the top-down approach and you don't want to exceed, you don't want to go under 1, you want to make sure that the value that you're tracking, if it's n, you want to make sure n never goes beyond 1. And if it does, then you just need to return 1 if it's a multiplication, or if it's a division. If it's an addition or subtraction, you just return the result at that point. So just basically like it's a limit check to make sure that if your n value goes under or over a certain value, you want the recursions to stop, and you need to return the appropriate value. So for multiplication and division, just return 1. Addition and subtraction, you want to return your temporary memory variable that you had keeping track of the value or your result. In this case, you just end up returning the result as of such. And answering the half and half approach, the half and half approach actually is the binary search algorithm that I explained earlier. and there are multiple implementations of this everywhere online if you need to actually see the code for it. But the algorithm is actually the easiest way to understand how binary search operates and how it does a half and half approach. Answered another question here where someone asked if top to bottom or down to up approaches are only increments and not division and multiplications, which is half and half. No. You can have bottom up approaches and top down approaches with multiplications and divisions inside of them. Like I said, if you want to use bottom up or top down or half and half, it's really your personal preference. You can use any one. It's just that, depending on the situation, one will always have the advantage over the other. The time complexity for this, did I give you guys the time complexity for a factorial function? Time complexity for a factorial function, basically because we have a repeated function factor. I want to give you an answer, but I want to give you the correct answer regarding this, so I want to make a note here on my side, and I'll answer it on the forum for you. That way I can remember to go about this. Notes, answer, question on time complexity, recursive factorial. I'll answer that question on the forum for you once we end the session for today regarding the time complexity of this function, and I'll give you guys a brief explanation as well as to how we went about determining the time complexity of this function. All right. Any other topics that we need to discuss? Right. Anyone else? Ask now or hold your peace. All right. So I'm not going to need codes for this in particular to explain this. So I'm going to write out the function here for you to explain why this is going to be important here. So when you're doing testing, and in particular you're asking about black box testing, you're basically going to have an int main function here. And then you'll have your first input parameter here being int argc, and then you have char star being a character pointer, argv, and this pointer is going to be towards the argv array. So that's what argc here is, and what argv here is here in particular, right? So what argc is, extract this out. What this does is that this keeps track of the number of inputs. So let me don't say inputs here. The number of command line parameters. And argv here, this is what stores the command line parameters. So this is your storage for command line parameter. Now, we see here that this is an integer, and this here is keeping track of the number of the command line parameters. Obviously, it needs to be an integer, right? So that's basic sense regarding this. We also see here that if this is going to be storage for the command line parameters regarding argv, and this is an array, as indicated by these brackets here, and it's also a character pointer, the array here stores the characters. So, characters. And that's like saying, okay, to give you an example here, let's say we had test.exe, and then we had 1, 2, ABC, and then XYZ. Test there is the name of our program. So that's, if we're counting our parameters here, this will be 1, 2, 3, 4, 5. And each of these parameters here is separated by a space. So argc in this case remember this is an integer, would be 5. Now let's watch what this is going to be regarding this for argv. Argv here is an array, indicated by the square brackets. But this also means that argv here being an array needs to also have a size. So how do we know what size argv is going up to? And this is determined by argc. So because we have these 5 inputs here, argv here is of size 5 as a result. So just to make this a little more syntactically correct, size of array here is 5. That means that there's going to be 5 things in the array from our inputs that we have here from the command line. So that means that if we have size of the array here as being 5, so that means this is going from 0 to 4. Argv of 0 here will be test.exe, being our first parameter. Argv of 1 would be 1. For 2, that'll be 2. For 3 here, it will be ABC. And for 4 here, it will be XYZ. So that basically gives you an idea of how each one of these parameters here, when you type it on the command line, how it ends up getting stored as a result. argc here is an indicator of how big we want the argv array to be, depending on the number of inputs we had from the command line. This argc feeds into our argv programmatically in the background to determine the size of the argv array here and how much storage is required to store the contents from our input that we placed in the command line. Each input here is separated by a space. So anything that's separated by a space is treated as its own command line parameter. So this one here being the first instance, because we're going from 0 to 4, this is stored as argv0. The next instance will be argv1. The next instance here will be argv2. The next instance will be argv3. And the next instance here will be argv4. The reason why we have this, the reason why we have this as a character array is because all these inputs here that are coming from the command line are characters. That's why we need to make sure that it's a character array. And if you can remember, in arrays, in order to access any array here, where there are multiple characters being stored as a result, you're going to have to end up using a pointer to the array. That's why you have character pointer instead of your normal char. That's why you use a character pointer in order to access the contents of this entire argv array storing characters. So this 1 and 2 here, those are not integers. Remember, that's coming from your keyboard, and that is stored in character formats. And because they're being stored in an array, if you have multiple characters like ABC and XYZ, the only way to access this is by using a pointer to the array. So that's why you need to use that character pointer here as a result. argc here feeds into argv programmatically in the background to indicate, okay, what is going to be the size of our argv array to store all of these command line parameters as a result. Yes, black box testing must be done using those parameters for int main. Black box testing is like if you have the final program, you have no access to the code, and you can only test the final program. So if you're designing any program that needs to be black box tested, you must have those input parameters no matter what. And you'll be testing them via the command line and using the batch scripts to automate the process to test each scenario or test case. All right, any further questions? Yes, as a safety net, you will have to end up using try, catch, and throw to make sure that your program does not crash. You'll try to anticipate for like incorrect inputs and so forth. It's somewhat impossible to get everything on the first run. So as you keep on testing, you'll end up getting ideas of what you also have to put for the exceptions in order to catch certain types of errors. So the main reason for using the try, catch, and throw statements is to make sure that your program does not crash. Alright, so private members in terms of get and set is that basically when you're using get and set in particular, it's a dedicated way for your class to access those private members, because once you use that private access specifier, it's such that nothing outside of the class can access it as a result. So if we had class test, and then we had test here being our constructor, tilde test here, being our destructor, and there will be public. We had get value, and we had set value in val or something like that. And all the way underneath, we have our private variables, which will be like in value as a result. And let's close off our class here. So, alright. So remember, anything here that is private is local only to the class itself. So if we had like our main function here, and let's say we created some object instance, so let's say test object 1, and if we said object 1.val, this won't work because of this private access specifier. The private access specifier means that only certain things in the class can access it. Anything outside of the class, be it in another function in another class, cannot access it. So the only way to go about doing this is that we need to make sure that we have a method here in the public access specifier in order to get and set these values. So that's why we need to have get value here and set value here being mapped here to public as a result. And these public methods can go about accessing this private member variable in our class. Now, let's say for instance, if we had get value and set value here, and I'm just playing devil's advocate, instead of this being public, let's say if this was private. If it was private for everything here, then there's no way that anything outside of this class can be accessed. So if we try to say object 1 get val, this won't work. And the reason why this won't work is because of everything here being private. So that's why you need to have your methods being public and your data variables being private, because your methods being public will be like the interface that is required for you to access your private member variables. If everything there was private, you just can't access it whatsoever. It's just going to stay inside that class and only inside that class. No other functions, no other classes will be able to access it whatsoever. Doing it, get back to my current state where I was. Nice. So anything here that's defined as public is going to act as your interface to the class. So this is like similar to like if you're in a company and anything that's public here will be like your receptionist or your front desk person. And the private here will be any sort of data that they can access only. No member of the public will be able to access it as a result. Sorry, I'm saying that confusing the terms. No one outside of this class will be able to access this private data as a result. So this public here is like, these will be your receptionists in your company, and only the receptionists here have access to this private data. Anyone else outside of the company here will not have access to this private data. So that's a nice analogy to think about regarding this. So the same thing, analogy maps back to your class statements here. Anything that is private in the class cannot be accessed outside of the class. And in order to access these, you need to have a control interface here, being your public methods within your class. All right, nice. Okay, so that basically brings us to the end of today's session. And I suppose you guys will be heading over to Akash's section in Blackboard Collaborate at 2 o'clock. So basically what we covered here were basically your misconceptions regarding the class interface here, the recursion methods, if you decide to go top down, bottom up, half and half, how you go about formulating your recursions, and seeing how you can go about formulating your orders by spotting the pattern that's kept on repeating. In particular, we observed for the logarithmic order at the start of our class in particular. Alright, so remember, quiz 1 is going to be starting at 9 p.m. tonight, and it runs for 24 hours. All the details for the quiz is on My Learning. If you do not have access to My Learning, and I know some people have already emailed me because of this, because of their situations, please let me know so that way I can make accommodations to you guys to attempt a substitute quiz later on due to your registration and so forth. Because I know the university administration, it's a little bit of a headache sometimes. So we will make accommodations to you guys as a result if you are unable to have access to My Learning and so forth. But the earlier you guys inform us, the better, so that way we can put these accommodations in place. For those of you who do have access to My Learning, remember the details of the quiz and whatnot is on the forum, so you can have an idea of what to expect regarding the quiz, what material you need to review, and so forth. As well as the details of the quiz, what is the format of the quiz, and how many attempts you are allowed on the quiz, and how your attempts will be graded as a result if you do your first attempt or your second attempt, and so forth. And until, let's say, until 8 p.m. tonight, you can still ask any questions. But from that point, you're going to be on your own regarding the quiz. Your group assignment is also going to be released at the same time, but your group assignment, you have 2 weeks to go about doing this. And the details for the group assignment of submissions and what to do and so forth already has been provided on the forum as a result. Alright, so that's it basically for today's session. Next week, Monday, we'll be continuing our sorting and searching algorithms lecture. And we'll also be moving on to data structures. In particular, we'll be revisiting stacks and queues and linked lists, if we happen to reach that far. But if we don't, we still have more than enough time to go about doing those sort of things. We are already ahead of schedule. So until next week, Monday, take care, be safe, and I will see you guys soon. And good luck on your quiz and your group assignment. Later.